it's Mrs. Scarpel, and we are going to be looking at exponential functions. Exponential functions are nonlinear functions, and they are in the form y equals a times b to the x. Notice x is what is now the unknown. X is going to be the exponent. A cannot equal 0, otherwise we wouldn't have a function. B cannot equal 1. If it were, we would have just a horizontal line. And B must also be greater than 0 when we're doing this. As x increases, the y value is multiplied by a constant factor. Remember, when we had linear functions, we were adding a constant value. With exponential functions, we are multiplying. So we have two tables to look at, and we're going to determine if it represents a linear or an exponential function. If I look at table A, as x increases, we see that it's constantly increasing by 2. As y increases, we see that it is constantly increasing by 2 as well. So because I'm adding the same value on my x's at the same time that I'm adding the same value to my y's, this would be described as a linear function because it has a constant rate of change. We are adding the same value. If we look at the second table, we can see that the x values are all increasing by 1. But it doesn't take long to look at the y values to see that I'm not adding the same amount. What I can see is if I take 1 times 3, and 3 times 3, and 9 times 3, I get the next value. So this is an exponential function. Because we have a constant multiplier. So with a linear function, you're adding or subtracting the same amount. With an exponential function, you're going to be multiplying the same amount. Keep in mind that even it can get smaller. The y value can decrease and still be exponential. That value would just be a fraction. Keep in mind that dividing by 2 is the same as multiplying by 1/2, or dividing by 3 is the same as multiplying by 1/3. Here we're going to take a look at evaluating exponential functions. When we evaluate, we take the value of x and we substitute it into our expression or our equation. So in this case, we have y equals -3 times 4. I write that just a little bit better. Times 4 squared. Order of operations says we do the exponents first, so we have -3 times 16. And then I multiply those. Y equals -48. For B, I'm going to change the 0.25 to a fraction. The fraction for 0.25 is 1/4, and that is being raised to the -3 power. And if we remember our properties of exponents, anything raised to a negative power can be written as its reciprocal. So 1/4 to the negative third can be written as 4 to the positive third. And 4 to the third is 4 times 4 times 4. That equals 64. And then 2 times 64 is 128. Now I just want to take a moment and show you how you can use the Desmos.com calculator. On Desmos, this icon is in the top of your screen. If you need to square something, you would just type 8. Let's just say I'm squaring the 8 and then the a squared. And you can see the answer right there right away, or just press the blue enter button. It's the dark blue with the arrow to the left. If you need to raise a number to another power, let's say we want to raise 5 to the 4th power, I typed 5, and then I want this a to the b button. And then if I do 5 to the 4th, I think that's what I said, we see the value equals 625. So we have an a squared button. If you want to raise it to another power, it's the a to the b button. We're also going to be looking at graphing, and in this particular set of examples we're going to look at in this video, we're going to be looking at graphs with a vertical stretch. So the graph of a function y equals a times b to the x has a vertical stretch by a factor of the absolute value of a. So it's the a value that determines the stretch, compared to the parent function y equals b to the x. When b is greater than 1, our graph will always be an increasing graph above the x-axis. When b is between 0 and 1, it will be a decreasing graph above the x-axis. When a is a negative value, that graph will flip to the other side of the x-axis in both cases. Also, what you will find is the a value of your equation will be the y-intercept of your graph. Because for the y-intercept, x is always 0, and b to the 0 power is always 1. So a times 1 would leave you with that a value. So a will always be your y-intercept of any graph of an exponential function. So let's take a look at how we graph these. We are going to use tables. So here we're going to look at an example when b is greater than 1. And my parent function is going to be, I'm going to just write this off to the side, and I'm going to call it f of x. The parent function is going to be just 2 to the x. And we're going to compare that with 5 times 2 to the x. So let's complete the graph for 5 times 2 to the x. 5 times 2 to the negative 2 is the same thing as saying 5 times 1/2 squared. Well, 1/2 squared is going to be 1/4. 5 times 1/4 is going to be 1.25. We can use the decimal values when it comes to graphing. 5 times 2 to the negative 1 is the same as saying 5 times 1/2 to the first. So 5 times 1/2 is 2.5. Then we have 5 times 2 to the 0. Well, that's just going to be 5. That's going to be our y-intercept. Then we have 5 times 2 to the 1. That's 5 times 2 is 10. And then we have 5 times 2 squared. 2 squared is 4, times 5 is 20. So let's plot those points. So when x is negative 2, we're at 1.25. At negative 1, we're at 2.5. At 0, we're at 5. At 1, we're up here at 10. And at 2, we're up at 20. And then this is a nice smooth curve, and it's not going to cross the x-axis. It'll get really, really close to the x-axis, but it won't cross it, and it won't ever equal 0. Now let's graph that parent function. So that's just going to be the powers on the 2. So 1/2 squared was 1/4. So when x was negative 2, we're at 1/4. 2 to the negative 1, or 1/2 to the first, was 0.5. 1/2 to the 0 is 1. 2 to the 1 was 2. And 2 squared is 4. And you could keep going. 2 to the third is 8. 2 to the fourth is 16. And we won't be able to put any other points on our graph because 16 times 2 would take us to 32. So the curve in red is our parent function. What we are going to do now is compare 5 times 2 to the x to our parent function. They have the same curve, or same shape, I'm going to say. But g of x has larger values than the parent function. Oops, just about misspelled function. For the domain, we're going to look at the domain of our graph of g of x. And remember, domain is the set of x values. Notice on the graph I have arrows on each end, which indicate I'm not ever stopping. This curve is not ever going to stop. We're going to use all x values, so our domain is all real numbers. The range, if we remember our work from before when we talked about domain and range, is the set of y values. And if we look at our curve, remember I said we're not crossing the x-axis, we're not equaling, we're not getting right equal with the x-axis, we're always going to be just above it here. So our range is always going to be, in this case, y greater than 0. Our curve will always be above that x-axis. Let's take a look at our next function. In our next function, we just have a -1, so our negative. So our a value is -1, and our b value is between 0 and 1. So and I'm going to use the fraction again. So we have -1/4 to to the negative 2. So I can flip the 4 to the squared, and because the negative is outside of the parentheses, this is going to be negative 16. And then we have negative 1/4 to the negative 1. So we would flip that. It would be a 4 to the 1. And the negative outside is negative 4. Negative 1/4 to the 0 is negative 1. Negative 1/4 to the 1 is negative 1/4. And negative 1/4 squared is negative 1/16. So I'm not going to be able to plot when negative 2 is negative 16, but I will be able to plot negative 1, negative 4. I will be able to plot 0, negative 1. I will be able to plot negative 1, negative 1/4. And it might seem to be nearly impossible, but I can plot negative 1/16 as well. And we can give ourselves a bit of a curve here. Now the parent function, I'm going to call it g of x, is just going to be the 0.25 to the x, not the negative. So instead of negative 16, it would be a positive 16 at negative 2. Instead of a negative 4, it's a positive 4 at negative 1. At 0, it's a positive 1. At 1, it's a positive 1/4. At 2, it's a positive 1/16. So we have a curve like this. So if we compare our graphs, we should see we have the same shape, but we have a reflection across the x-axis. Of the parent function. The domain, remember domain is all of the x values. That's going to be all real numbers again. And we're looking for the domain of our blue curve, the domain of negative 0.25 to the x. And that curve is completely below the x-axis. So that's all of the y values less than 0. So if we have a negative a value, we're going to be reflected across the x-axis. When b is between 0 and 1, we have this curve that's actually decreasing. In your assignment, you may be having some graphs that will have some stretch to it as well as a reflection. But it's always important to use a table and plot some points.